This is the third video in a sequence which talks about eigenvalues and eigenvectors. Okay. The first video was about the definitions and doing computations to basically verifying eigenvalues and eigenvectors. And in the second video, we talked about determinants. Okay. And in this video, we're going to put the first two videos into practice to actually find the evals and the eigenvectors. Okay? So let's go through an example, and then the rest are for section 3.2 in our textbook are pretty straightforward. Okay, so let's consider, for example, the matrix A. Okay, could be the matrix 3, 0, 2, 1. Okay, and you should be considering this matrix A as building the right-hand side of the differential equation. So what we would be considering here is a differential equation dx dt is equal to 3x, a partially coupled system. dy dt is 2x plus y. Okay? And all we need to build the solutions to this differential equation are we need to find two solutions y1 and y2, and then we can make our solution y as a linear combination or superposition. Okay, so the first step would be to find some y1 and y2s, and then the second step in section 3.2 is to do the superposition principle. Okay. So the whole reason we're finding eigenvalues and eigenvectors is to find y1 and y2. Okay. So let's consider this process. Recall from the first definitions video that the equation of importance is AV is equal to lambda V. If you can find for some lambdas, the equation AV equals lambda V has non-zero solutions. Okay, so it's the non-zero solutions that we're interested in. But we don't know what values of lambda this equation has non-zero solutions. So the thing to consider here is that you're going to rewrite the original equation. You're going to subtract this equation from both sides, lambda v from both sides, and then you're going to rewrite that as lambda times the identity matrix times v is equal to 0, where, for example, what we mean by lambda I is the identity matrix 1, 0, 0, 1 times the number lambdas. So this would be put lambdas on the diagonal of this matrix. Okay. And then notice that they both have a v in common, so you're going to factor out the v. And we would say that solving this equation, solving this equation is equivalent to solving this equation. Okay? And remember that we're looking for a non-zero solution. That is the goal here. The only way you're going to get a non-zero solution is if, from the determinants video, that the determinant of a minus lambda I is in fact equal to 0. Okay? And this will essentially right here give you an equation, gives an equation to solve for the variable lambda. If you can solve this equation for lambda, then you have your eigenvalues. Okay? So the problem becomes equivalent to finding the determinant of a minus lambda I, where a is 3021, that was given from the original problem, and you're going to subtract lambda on the diagonals to make a new matrix, 3 minus lambda 0, 2, 1 minus lambda. And it's this equation, this new matrix right here, that you need to compute the determinant of. Okay. the determinant of that will be the two diagonal entries multiplied, and then you're going to subtract the product of the off diagonals. So you'll get, in this problem, 3 minus lambda, 1 minus lambda, minus 0 times 2, which leads you to 3 minus lambda times 1 minus lambda. And this is what you wanted to be equal to 0, because you wanted to find non-zero solutions for v, for your eigenvector. The solutions here for lambda are 3 and lambda is equal to 1. These are your eigenvalues. Once you have your eigenvalues, it becomes necessary to go back and find the eigenvalues. How do you find what are called the associated eigenvectors, or what are called the eigenspaces? Okay, so let's take a step to the next page then, and we will consider the associated eigenvector problem. Okay. So you'll recall that the matrix A we had was 3, 0, 2, 1, and we found eigenvalues for that problem of lambda is equal to 3 and lambda is equal to 1. Okay, we found these by computing the determinant of A minus lambda I, the identity, and setting that equal to 0, and you solved for lambda. Okay. The thing now is to return back to AV equals lambda V. Remember, now you know all the possible values of lambda. The only values of lambda which have non-zero solutions, having non-zero solutions to AV equals lambda V, are these two values. That's it. What were those non-zero solutions? Well, you need to look at A times V is equal to 3 times V, right? And then solve for V. Okay, now that you have the eigenvalues, can you go ahead and find the associated eigenvectors? This will be equivalent, AV equal 3V will be equivalent to A times XY is going to be 3 times XY. And you need to figure out what X and Y are. Right? But we know that the matrix was 3, 0, 2, 1, XY, and we need to again set up a system of equations to solve. This leads you to 3x is equal to 3x, and 2x plus y is equal to 3y. Now remember, we're going to have non-zero solutions, right? So you're always going to have something weird happen here, and it's this first equation that seems kind of weird. 3x is equal to 3x. This is weird in the sense that any value of x works. Okay? And that's okay. If any value of x works, then let x be equal to anything. Right? And typically we call that anything also x. That will lead you to 2x plus y is equal to 3y. Turns out then that 2x will equal 4y, which will imply that y is equal to 1/2 of x. Which says that your eigenvector v, the solution to AV equals 3v, is your eigenvector. And x could be anything, and y is 1/2 of that anything. Right? So recall that a possible eigenvector is x multiplied by 1 1/2. 1 1/2 is a possible eigenvector, or -1 1/2 is a possible eigenvector, or 2 1 is a possible eigenvector, just choosing different numbers for x. Okay. So what we say here is that the eigenspace in the xy plane, our eigenvector was 1, 1, 1, 1. Okay. 1 in the x, 1 in the x, and 1/2 in the y. Or you can go a full step, 2 full steps in the x direction and 1 step up, right? That's just a vector that's in the same direction but twice as long. Here is 1, 1/2. Here's the vector 2, 1. You can also have eigenvectors back this way, right? So for example, x could equal -4, in which case your eigenvector v would come out to be -4, -2. So 1, 2, 3, 4, -2. Right. Sorry, not quite a straight line, but they should be a straight line. So here is your what's called the lambda equal 3 eigenspace. Any vector along this line is going to be an eigenvector associated to the eigenvalue of 3. Okay. So now that you know how to find the eigenvalues and the eigenvectors, you can then, proceed on, for example, to say that your y1 of t, in this case, could be e to the 3t multiplied by the eigenvector 2, 1. So one of your eigensolutions could be 2e to the 3t, e to the 3t. That is your y1, and then you can proceed on as we've done in class to find y2, using the other eigenspace and then finding the solution y. Okay. So that ends this video on how to compute eigenvalues and eigenvectors, and you can now pick up the problems from the textbook.